Okay, with that set up, where the recordings are going to go, I think I'll just plug it right up here. I'll just call it recorded R session, something along those lines. And it's going to direct you to a YouTube playlist where you can find the file. Well, welcome back again, folks, to now the R and RStudio side. Other thing I should mention right away before we get too far is the environment that I'm working on is kind of limited in its resolution. I wish we had two monitors, but there's a lot of stuff you can't really quite see too well if you're coming in through Zoom. This is what my screen actually looks like. It's really pretty full. I've got this panel right here that I do have to minimize, unfortunately. I move it over here to the right, and it just shows who's talking. Then the next thing I load in is a window that looks like this. So when we get going, from my point of view, what I see is this all, okay, that's getting, yeah, about right. Let me try with a less crazy looking screenshot though. When we actually get going, this is the view that I actually see the class through. So I don't have a separate monitor to show the participants. Instead, I minimize it to here so I can see who's talking. I can also see this control panel to see any reactions that you put out to determine who's talking, that kind of stuff. And then all of our work is going to be somewhere out here in the middle. So that's going to be the layout. And another thing we should do before we get started is definitely discuss this document right here, or this link. Were folks able to get this working, both R installed and RStudio installed? If you haven't today, that'd be totally fine as well.
I downloaded them. I haven't opened them though. I think I did it.
Okay, sounds good. If you've got them all downloaded, you should download it. You should be in good shape. Let's just run through this really quickly to see what it would look like. So we go to this link here, where it's actually directing us is to RStudio. This is using the actual program R, but then RStudio itself is the integrated development environment, much like with MATLAB, when you have all the extra bells and whistles showing you a script region with syntax, a region with your loaded variables in, and all sorts of extra things. This is what RStudio does. It's not as if R alone is a bad product, but you have to know R really, really well to work with just R. So think of this as just a way to bring in a whole bunch of ordinary life improving things that you would expect for a good computing environment. What you would do is install R first, like you mentioned. Then there's several options. I think most people are going to be going to the Windows distribution. If you have Mac OS or Linux distribution, use these other links right here. For Windows, pretty much for the purpose of what we're doing today, the base package is all you need. So you would click on that, download this file, and this is where I get stuck. I can't actually open and install a file on this desktop computer. It's too locked down for that. But that completes that one step. When you go to install that, you then have this. So this is your R icon. And what I would do if I could is put it in the recycling bin because it's just a shortcut. This is not the actual icon we're using. So when you go to install R, you probably do want to delete that or deselect the option of putting the shortcut on your desktop. The thing we're actually using is this icon here, RStudio. And we get to that by closing this out. Going to step 2, install RStudio. There it goes. And it didn't ask you too many questions. So if you're on a Windows machine, that is the right install file. Run that one. It'll provide you with this link on the desktop, and you're all set. But if you're on a different distribution, it doesn't work on iPad, unfortunately, but Mac OS and everything else. Just scroll down, and you have Mac OS, other Linux distributions as well for the install file on RStudio. So if you run that file, then once again, you end up with that icon. That's the one that we're actually going to use. Any questions, folks, on just getting to this step, getting that install up going?
Yeah, thank you, Ben.
Yep, absolutely. Well, for next, let's just open it up. Here it is, RStudio. Taking a moment. There it goes finally. I might have opened it several times on accident. We'll find out shortly. I'm going to ignore all warnings. I really need to get this updated, but impossible to do on this environment. Looks like I was doing some stuff here already. The neutral environment probably looks a little bit more like this. Ordinarily, I'd maximize it, but again, my screen is kind of busy on the fringes. I have all sorts of zoom controls going on. So I'm going to run it kind of about like this, as maximized as possible, really, for the screen real estate I have. Let me delete all that out. This is what the neutral environment would look like in RStudio. In fact, it probably looks a little bit more like this. All you've got is a console, some empty environment here on the right, nothing down below. You can resize these things as necessary, left, right, up, down, and so on. But probably the very first thing you want to do is click on this icon right here. The shortcut is Control-Shift-N. Open up the R script, and this is a big fundamental way we're going to be working through RStudio. Down below is just for quick computations, much like we were looking into with MATLAB, like 2 plus 3, that's 2 times 3. This is a nice interpreter language where we just input results, hit enter, it evaluates, compiles, gives us results. But we'll be doing a lot of work right up here as well, developing the script to solve the problems that we're looking into. So that's the environment. And the next link down here is definitely optional reading, but if you're curious on why we're using RStudio, when maybe for an example, you know Excel can do lots of statistics, just about everything. The purpose of RStudio itself, here's an article talking about it, but these are my words right here. The main use of RStudio is due to the fact that it's considered to be industry strength for statistical computing. More important than that, it's also completely open source. So this package, RStudio, is not just about the fact that it's a strong computing environment. It also brings together a humongous community of people who code in R all the time to take on data science problems. And there are lots of independent packages for using R together with RStudio. And another thing to think about is Excel is highly limited, 17 cells per sheet. That might go up each year as they make the program a little bit more powerful. But this is actually pretty severe as a limitation depending on the kind of data that's being handled. Governmental agencies, biological data sometimes is in the terabytes to petabytes range. And you run into limitations with Excel just immediately on that. R, however, is a lot different. It can be ran in a lot of different types of computing environments. You can get some scientific processors with major amounts of cores, huge amounts of RAM. Even if you're in the petabyte range or beyond, we just make a big system that can handle that amount of compute that we need to deal with. So that's the idea with R and RStudio. It's massively flexible, open source, and wildly powerful because of that. As an actual language, it's not the most efficient in the world, but it gets the job done. So that's the environment. That's the overview of why we're going to use it. And I thought for demonstrating its use, a good way to start off is just throwing a problem at it. So this is the practical problem that we're going to take a look at. PDF file and a Word file just so that you have compatibility for opening this. And here's what it looks like. Again, it's a really practical problem. So you might imagine something like this happening to you or a relative or someone that you might do statistical consulting for. It says we have property bounded by perpendicular roads. So that's the north road, that's the east road bounding this property in the middle right here, and a stream that runs along with it as well. So kind of an annoying situation. We'd want to know a lot of things about this property. In particular, if we're maybe doing an insurance quote on this, we would need to know the area that we're insuring. How big is this property? Everything is measured here in feet. So we're going to find the area of this property in feet squared. But, you know, there's lots of ways to do this kind of problem. One way you can think about this is draw a diagonal down. Think of this as a right triangle. And just do a really crude back in the envelope kind of computation. We can find the area of a right triangle. And then we'd say the area of the property is a little bit more. That might be okay for some people, but if we're actually working for an insurance agency to get this in property insured, we need to do a lot better than that. So that's where the problem is going to start. Trying to find out how to compute the area here of that property. Any questions about the problem itself before we launch into it? Okay, let me close this temporarily. Well, not temporarily. I have the same Word file duplicated over here. And any work that we do on this, I'm going to save and just drop down as two other files, another PDF, another Word document, but they'll be the solutions slightly indented. So let's start this out. This is the problem we want to solve. Oh, sorry for missing a chat. Thanks for letting me know. And in solving this problem, first thing we'd have to do is import this information some way, somehow, into RStudio itself down here. Usually that's a process where if you had the data file itself, you would just click on this, import the data set directly. And we'll do that for some of the other problems that we take a look into. But for this problem right here, we have to do a manual data import. We're just going to type this in directly. So we have pairs of coordinates. We're doing a regression analysis on these black dots you see here, trying to get a curve, which will be our stream. And for that curve, it says here, fit a degree 4 polynomial function to the path of the stream. So here's how we'll start. Let's first do this separately, import all the first coordinates, 50, 0, 50, 150, and so on. Then we'll import all the second coordinates. For the first coordinates, we can call it x. So that's us defining a variable now. And there's lots of ways to define this variable. X equals, in fact, works. But for people who code in R a lot, it's often written this way. X left arrow. The left arrow here is a way to say X gets the information that we're about to supply to the right. So I'll often type it out this way, and I'll often just read X gets, and then whatever we put over here. So now let's put in that information. If we put in X gets 0, run the whole syntax, this is how our environment's going to change. Oftentimes when we're running the syntax, you can select everything with the mouse, click on the run button, and it'll run it. Or another way that I'll often do is hit Control A, highlights everything in the script region, hit Control Enter, and it runs everything. Down below in the console, it just tells you what you ran. We ran X equals 0 twice, it looks like. Over here on the right, it says, we have a new value, X, and it contains inside that, well, just one element, 0. It's not quite good enough for us. We need to combine all of the other X values. And so this is our next step. This doesn't work, but sometimes it's pretty informative to see why things don't work, what the error message would be. And it seems logical, right? If you want to combine a whole bunch of X values, comma separate them, that in fact is right. There's one thing missing here. We hit Control Enter, Control A to highlight everything, Control Enter to run it. It says unexpected comma and X gets 0. So nothing actually happened whatsoever with this syntax. But there is a big fix. We need to go over here and combine both of the values together. Anyone happen to know how to do that if you've used RStudio before?
Would it be square brackets?
It would be a square bracket, but you're on the right track. We're going to use an open parenthesis for the input on that. And we'll only use square brackets if we want to access an element inside that vector X. But yes, you're on the right track. We need to wrap this around with something. So parentheses do the job. But even that's not enough. If we run this, same kind of error, unexpected comma. The thing that's missing is, we'll think about what we want to do. We want to combine both of those values and then the other values we see down here into one container. And that's the solution in R. Lowercase c to combine them both into one vector x. Kind of silly in a way, but this is how a lot of coding in R Studio goes. If you can imagine what you're doing and just say it out, you're probably saying the syntax all at once. Paraphrase to just C for combine. Hit Control A, Control Enter, and new line from our syntax didn't output an error. And now notice what happened in the global environment. X is now indicated to be numeric as a vector of size. One column, 2 rows. The elements inside are 0 and 50. Down below, if we type out X and import and hit enter, it just outputs what X is. If we go X with a bracket and 1, then we're just talking about the first entry in what we're thinking of as a vector X. So it outputs 0, X bracket 2 would output the second element 50. If we do something crazy like X bracket 3 and there's no third element, it just says NA, not a number, not applicable is kind of the thought on this. So that's the name of the game. To import the data, we're just going to throw in the first coordinates, comma separate them, wrap them around parentheses, and say combine all that information. X coordinates are kind of nice. They increase by 50. So let's type these all in at once. Kind of challenging to fit everything in, but we'll do the best we can with this. Then X 300, 350, and 400. Spaces I'm putting in are not necessary. Every bit of white space RStudio reads through until it gets to the non-white space elements. So comma separating with a space is just a way to be able to visually see if it looks like it's all accurately put in correctly. Then we just do it all over again. Let me resize just a touch. For the Y data, we need to be a little bit more careful. It's all the second coordinates, but they have to be put in order. I put 390 in first. It would be relative to the input 0 as the first entry there, and suddenly we don't have the right regression whatsoever. So going in order, which is a little bit jumbled up with some of these, let's carefully put in Y gets combine 540, 390, 390 twice, then 430, 425, 360, and let me move this around, 275, 125, and the last one is 0. So that looks like all of our coordinates. Let's see how accurate we are. Just run this and see if the size of both of them are going to come out the same. So hit Control A, Control Enter, and we have 2 numerical vectors. They're of both size, 1 column, 9 rows. Doesn't mean we typed it in verbatim accurately, but at least it's got the right number of elements. So there it is. All of our information's imported. And there's a lot of stuff we can do with this right here, just to demonstrate RStudio. But we don't want to go too far off the rails. We want to also solve this actual problem, even if it takes a day and a half or something like that. So I'll just demonstrate a couple of uses of R just down below in the console. If we were more curious about vectors X and Y, we can write out things along the lines of summary X. And it gives us a lot of information. The minimum is 0, the maximum is 400. The median, that's hard to highlight. The median, which is the 50th percentile, is 200. The mean, this is the arithmetic mean, or the average, is 200. And these are the 25th percentile and the 75th percentile of the data. 300 being the 75th percentile means approximately 75% of the data is below that figure, for example. Do it again on Y, we have summary, Y, and just a different set of values here. Notice this time the mean, which measures the center, is at 390, but the mean, the average, is 326.1. Tells us something about this data. The sample mean is pulled to the left, so there's a little bit of a skew on the Y data. If you want to look into that a little bit more closely, lots of graphics we could produce for either vector. We could go hist for a histogram. It outputs the graphics over here to the right. kind of hard to get a good window on those graphics, but if we really needed it, we would click on export, copy to clipboard, and from here we can resize the data as we see fit. Again, we didn't need this information as much for the problem we're trying to solve, but this is just a really fast demonstration of some of the statistics and data visualization we can do just right away now that we have data. And notice this data has a main peak of concentration right around where the median value is, 390, and it trails off a little bit further to the left than it does to the right relative to that mean peak. That's why the sample mean is a little bit lower than the median. Sample mean follows the direction of where it's trailing off, where it's skewed towards. Oh no, didn't mean to close that whole environment. Let me reopen that again. RS from a Windows is a fast way to pull that up. I thought I was closing just the plot, but the good news is with RStudio is it remembers the syntax. So if we just rerun this, we're back to where we were, less the graphic. So we're about ready for the next part of this. We're doing a regression problem. Let me actually open that again just to visualize it quickly. We're trying to fit a curve to this stream. First thing we should do is actually plot the points that we produced to see if it really takes on this basic shape. So that's where we go. Let's organize this a little bit better and say, here, the hash is now a comment region. So this is something not executed by R. Here we're importing the data. And on the next step, we're going to plot the data. And if you're plotting the data, what is the function? It's got to be plot, right? That would make a lot of sense. So let's just go plot X values against Y values. Hit Control A, now running everything. Control Enter. And we get an error. 5-figure margins too large. You may not have gotten that error, but I did because, again, I'm working on a very limited resolution screen space. My desktop is not even 1080p. And I've compressed the graphics down so far that RStudio had an error. It was not an R syntax error itself. So now after resizing this window, let's hit Control Enter again, and the data shows up. Again, it looks a little funny because everything's compressed down. So hit Export on it. We want a better view. Compare this against what we saw on the actual graphics. Take a look. Just fighting with the windows. Let me see here. And yeah, I would say we've got about the right shape here. The scale is a little bit different. I've kind of compressed it to not square at all compared to what this was. And this doesn't look like it was a square scale either, but it has the basic shape that we're expecting. So we're definitely on our way with this. We have the visualization. Now we need to do the regression. We are coming up with a polynomial that gets as close to many of these points as possible. Whereas close is all about the residuals. And at the same time, this is kind of a challenging problem. We don't want to get too bogged down into the actual statistics either, because regression analysis is a 16-week actual class at ISU. We're just looking at, if you're doing this problem as maybe an assignment that was given to you, how would you take it on using technology? So we're going to move on to the next step of constructing the regression model. This is where things get a little bit tricky in a certain sense, but we'll make our way through it. Any questions at all, folks, getting to this point?
Thank you.
You bet, absolutely. Well, let's go up to then the next step. In constructing the regression model, we want to store actually the whole output to the regression. So here's what it's going to look like. Let me just try to resize this a little bit more. Let's call it model. There's something short. Model gets the output of LM. That's our big function, RStudio for regression analysis. This stands for the general linear model for regression. Now, next, it tells us how you would use that model. RStudio is trying to be helpful, but this is a pretty complicated function, a lot's going in. We'll write it out this way. We're doing a regression on the y values. We're trying to model the heights of these dots that we see here. We're regressing against the x data right here, but we're also doing it as a polynomial function. So maybe before we get right to specifying the model, let's come back to this in a moment. Let's actually say what the degree of that function should be. Degree gets, we know that we're going for a fourth degree polynomial function, but on our way to getting to that fourth degree function, let's see how the model looks at when it's linear, when it's quadratic, and when it's cubic. So let's start at actually degree 1 and then work with the model, see the changes. This is kind of annoying in a certain sense because the actual polynomial model that goes to the right of that tilde, and by the way, the tilde is right over here to the left of the number 1. It's going to be a polynomial and its format changes a great deal by its degree. But here's where we have another bit of syntax. Call this, let me double check my syntax, poly. Inside here, pass to it x. So that's the polynomial function that is going to take on the x values. Also pass to it degree, starting at degree 1 right here. Close that. Close out here. And I think we're all set. One small change I do need to make. When you're doing a regression analysis, this is loads and loads of linear algebra. And there's weird concepts along the lines of orthogonal polynomials. We actually don't want that because dealing with orthogonal polynomials takes us a lot of extra work to actually see the plot. We have to unpack those coefficients, express them in the right way. So one extra thing we're going to put here is raw as a parameter equals true. Let's highlight there. If true, it says in yellow, use raw and not those orthogonal polynomials for linear algebra. The orthogonal polynomials are more numerically stable, easier for the system to work with, and that's why it's defaulting to true. But it's not easy for us to actually work with that output. So let's set it to false right here. I think that's going to do it for us, folks. Let's run this to test it even works, see if we missed anything like an errant comma. Hit Control A, Control Enter, and let's see the change over here. We've now stored the degree, which is going to be something that we fluctuate, the x data, the y data, and now a model appears. This is a list of 12, so if I click on the play button, it gives me a whole bunch of information which is vital, but not something that is meant for me to read. This is just the output of all the math that went under the hood of fitting this linear regression because degree was 1. So instead of looking into here, what we usually look into is, much like when we were doing summary X to look at some basic statistics, we do summary model to look at some basic features of this model that we just produced. So summary model is doing that kind of investigation. Well, let's run this all out, see what happens. I'll just scroll down to this last part right here. Control A and Control Enter gives me a whole bunch of errors, probably because of the graphics again. Let me raise that up. There we go. We didn't have any errors this time. Now I need another challenge of getting this all to fit on screen. And let's see what we just did when we called summary model. Let's see here. Summary model starts right here from the syntax above, and it outputs all this information. Information on the residuals, information on the coefficients. This is the y-intercept for the linear equation, and this is the term for the degree 1 term. So the whole model that's going to plot a line through these data is going to be 326.11 minus 420.22 times x. So that's our linear equation model. Lots of stuff to discuss here. There's a whole bunch of things about, say, a test statistic, the degrees of freedom of the model, p-values. This is the statistics that we could go into a long sidetrack journey discussing. But we also have something for multiple R squared and R squared adjusted. Just to streamline what we're doing here today, focusing on the actual computer algebra system, that's the most important number that I would want to discuss. It's adjusted R squared, so to me, this is a slightly more accurate value. And what it's representing is the actual amount of variation that is apparent in the second coordinate, the y coordinates, that's explained when we try to fit a straight line linear equation to it. Straight line linear equation is not a good fit in the first place. We need to curve this a little bit to capture the fact our data values curve. But if we try to do a linear equation that fits all those points as best as possible, it's explaining about 75% of the variation on how the coordinates move up and down the second coordinate specifically. And that's not bad, but we wonder if we up the degree, how would that change down below right here? Let's make that adjustment and take a look right away. Now we're modeling with a quadratic. We want to go up to degree 4, but at quadratic, the percent of variation that's explained by the now degree 2 polynomial function, which would probably be plotted something along these lines, roughly, it shot up a lot by at least 10%, it looks like. We're now at 86%. Well, that's kind of important to look into those, seeing what's happening with the model. If we try to do something just insane and say, fit a 20-degree polynomial function to all these data points, our studio actually complains about that and says, the degree must be less than the number of unique points. And, you know, that's a great thing for them to say. The model is way, way overspecified at this point. It's not even going to try to do this. We do something else that's outrageous and say 8. That's 1 less than the number of unique points, which was 9. Run this, and all sorts of problems again. Adjusted R squared, not a number. Multiple R squared is 1. The model's suffering even at 8 data values. Excuse me, at degree 8 is a polynomial function. At degree 7, now we start to get some normal output. And even though this looks like it's really good, we want to know what's happening when we were at degree 4. Why did we stop at degree 4? Possibly because the improvement of what we see here was not enough to justify the extra complexity in the model. But you know what would be really helpful with all of this? Is if instead of drawing curves, we actually plot those curves. So let's do that as well as our next step on this process. We don't just want to compute the model specified by the degree. Let's go back to degree 1. We want to see how it does visually over here, and then take a look at the adjusted R squared as well. So next thing we're doing is plotting whatever equation we get out of this model. I think this is the hardest part of the process. So before we start that next journey, any questions at the moment?
No, not so far. Thank you, though.
Yep, you betcha. Okay, let's go to that next part. Let's call this visualizing a polynomial regression model. And my goal with this problem is to kind of do it as a sort of live coding event. But I have to be honest with you, this is the part where I'm bound to make mistakes. So I have a big old cheat sheet right here. I'm going to try to minimize using. You see my eyes go to the left, then I'm looking at it for sure. Now inside this model is all sorts of stuff. Let's see if we can take a look at it again. But one of the things inside the model is the coefficients. We want to grab those right away. That's just the coefficients of the polynomial, this one's linear, that we're building. So let's call it COEFFS, coefficients, gets, just like we did a function with model after we stored the result of the linear model into model, we do another function calling model again. This one's going to be COEF for coefficients. We put an object in there. It says it's a generic function which extracts model coefficients. Sounds like it's exactly what we want. So go model. because we have false right here, we're going to get the polynomial that we think we're going to get, which can actually be plotted on this diagram. So running all this now gave us coefficients. There's only 2 here, but that's because we're doing this model as degree 1 linear. We did it as degree 4. There should be 5 coefficients, the constant term, and then a term for x, x squared, and so on. Let's see if that really adjusts. Yeah, at degree 4, we have 5 coefficients, which would be exactly what we're expecting. Let me reset it back to 1. So now that we have the coefficients of the model, we need to construct a function from scratch, an actual mathematical function, pulling in all of those coefficients. Let's give it a clever name. Let's maybe call it, how about, now that I'm on this step, I'm realizing there's a better way to actually plot this out. Before we go to build the function, we still need to build this function right here, but this is more for the purpose of telling R to integrate the function we build. So we need something right here in the middle. Sorry for the chaotic approach to this. Before we get to that step down below, let's put in a new step and call this visualizing the polynomial regression model. I just realized that means I should have controlled and pasted this out of here. And let's rename this to building a polynomial function. So this kind of coding is definitely pretty chaotic, but we're getting through it. First phase was data import. Second phase was visualization. This is a big phase where we build a model. And this phase, we're going to visualize what it actually looks like. The function we want is, I believe, called lines. It takes it for the input, these values right here. Our values up there are sorted, but if they weren't sorted, we would have to insert sort x. So we might as well do it here so that this syntax can handle more unique situations with unsorted vector x. Then we take our x values. And what we're actually doing is plugging it back into the model right here to get the predicted values out. Let's see, how do we do that? Lots of weird stuff inside here. Nothing that indicates what we really want, but down below here, well, rather in this location, let's go predict. This just says model predictions. It's a generic function for predictions from the results of various model fitting functions. Sounds like that's what we're doing. We're fitting the actual values. It's not going to give us the y values. It'll give us the y values after it's trying to fit it to the stream curve here that we're trying to regress on. So we go predict, pass to this. It needs a data frame. So ordinarily you can just give it x. Well, I need to go data.frame. And x would work, but we want to sort it as well. So sort x. But notice what RStudio has done as a huge help. Every time I open the parenthesis, it's closed it to the right. And as I move the cursor, it shows where this closed parenthesis is associated to the open one. Move cursor right more. Well, it didn't do it on that one. That's kind of rude. I guess I need a mouse key to show it. Left click on that spot there, and it shows this closed parenthesis relative to that location. And that one is relative to the very start. I'm not sure if this is right, so let's run it and see what we get out of all this. But I don't want to run that bit right there. So this is the point where I would use the mouse to select the region I want to run. And either hit Control A here, but if I've used the mouse, I'd probably just click on Run up here. Okay, did not work. Let's see what we got off here. Not applicable method for predict applied to an object of class data.frame. So I have one small issue with the predict function. Let me take a look at my cheat sheet here. Aha. So for the predict function, one thing I forget is it has no idea that I'm trying to pass x back into the model unless I make that an actual parameter that I pass to the argument of the predict function. Should have been modeled, going right here. Then I give it data.frame, sort the X values, and this should run for us this time. It's degree 1, so we should see a line going through the syntax. So let's select this field here, run it, and hey, that's a success. We have a regression equation coming through right here. Let's check the model as we upgrade to degree 2. Again, the R² adjusted value, 75% of the variation on the second coordinates for all those dots accounted just by the linear model. But there's a pattern of why some dots are above and below. This depends on where you're at in this curve. So if we change to degree 2, we hope that this pattern of some regions the dots are above, some regions the dots are below, vanishes. So hit, let's do this trick here. Let's comment that out. So that way, if we hit Control A, we'll just run the whole thing. But, oh, not that part. Commented that part out, that I got a little bit ahead on. Now hit Control A, Control Enter, and this is the degree 2 model now, a quadratic function. It does a little bit better, but there's still points in this region that are above. A little bit better on this region, a little bit better on that region. R² adjusted value has jumped a lot by around 10%. We're going for degree 4, but we're just seeing what happens to the model as we walk it up the complexity step by step. So here's degree 3 next. At degree 3, this is starting to look appropriate. We're decreasing, our curve has an inflection here where it starts to decrease even faster. And now, whether the point is above or below seems to be random mostly as we go along this curve. The R² adjusted value didn't go up by 10%, but it did go up by a lot. And now let's do this again. Degree 4, at degree 4, notice that it seems to be trying to practically connect the lines to each one of those dots. Not really, but it's getting really close to each one of these. And this has jumped to its last really big jump. This is probably why the problem asked for degree 4 model. We did go up to degree 5. It's not necessarily improving this very much. The curve changes a lot, so the area will change a lot. And if it's not going to give us a big improvement here, it means the polynomial equation we're getting is not really modeling the actual stream we want to have modeled. It maybe is getting close to the points, but it's not doing in practice what we really want. So at degree 5, run this whole thing and see how it jumped by, looks like less than 0.001, less than 1,000. So this increase of complexity didn't really improve anything about the model. And so it does mean it really sounds like it's a good idea to leave it at degree 4, with that still very high amount of variation being explained by the model, just about everything. So we've got our visualization. We have the degree 4 model. This visualizes it. And if I uncomment that, this grabbed all of the coefficients of that model. It's right here inside coefficients, COEFFS. Hang on here. We have an intercept and then some other values here. It's kind of a interesting way it outputs. But you know, if you really want to look into these coefficients, oh, hang on. I was expecting this to update to 4. Let me rerun this again. Excuse me, update to 5. There it is. So we have 5 coefficients altogether. Let's rerun COEFFS. And that looks a little bit better. Here are the 5 coefficients. The intercept would be this value. Here, when it says 1, this is the degree 1 term. So we would take 326.11 minus 420.21 times x, minus this value times x squared, and so on. From this information already, we could just get pencil and paper, build out the polynomial equation, and just integrate it by hand. But you know, that's the silly way of doing this, right? If you have everything already stored here, what we really want to do is actually build the honest polynomial function. We're going to use a couple extra structures there in a for loop to do that. Then we'll make RStudio integrate that function as well. So those are the next things that we're going to be looking into. I don't think I can do all of that in 3 minutes, but hey, we made a pretty good start on this. Any other questions or comments so far, folks, with where we're at right now on this problem?
No, I'm good.
Okay. Well, these problems are kind of tricky since I don't necessarily want to break a problem in half, but they're long problems as well. So what I'm going to do here with where we ended on, let me just take this as a screenshot. This document is going to change as our solution gets built up more and more. Let's call it solution so far. We ended on this screen here. But the other thing I want to share each time we do something in RStudio is all of this. This is like the really, really important stuff. Word of warning though, if you paste syntax into something like Microsoft Word, that's not super dangerous because you can take all this, copy it back into RStudio, and you'd be totally fine. But there is a context where this doesn't work out. If at any point we have to type out those quotes right there, they are not the same as those quotes right there. And I mean, it's hard to see, right? They look the same. If you copy this into RStudio, the whole thing breaks down. So one good takeaway for this is I'm throwing this all into the Word document just so it's available for us. But as a warning, never write syntax in R. Use Notepad or Notepad++ or the syntax field in R itself, or RStudio is where that would be. So you can copy data out of here, but you would never, ever really want to write anything inside here for syntax. These would be better options. But I think this is a good stopping point for us today then. When we come back, that's kind of weird, already a week away from today, we'll refresh what we did, keep on going in this direction, and then we'll probably have a lot of time left over. We'll look into the next problem to start working on. Probably something where we have to actually import a big data set, a huge data frame, and then do some data analysis is my thought for the next problem. But thanks for hanging out, folks. Thanks for participating. I'll get this saved up. It'll take me a little bit of time, but I'll also post that link to the videos right over here for each one of them that we produce. But have a great afternoon, folks. If any questions come up about any of the stuff we did, any of the stuff we did, you can look up my email address on the syllabus. I'll be happy to discuss. But I'll see you all next week.
Thank you.
Thank you.
Thank you.
Take care.
Thank you very much.